Hi everybody. My name is Natalie, and this is our group's presentation about solar cells for our chem final.
Yeah, the base element that is used in most solar cells is silicon. It's a large component of the cell. It's in the metalloids right below carbon, so that means it has four valence electrons, and it's used as a semiconductor in the cells, which means that it's not a very good conductor, but it does conduct electricity. Um, and they use basically small squares of silicon. They're about 15 centimeters in diameter. I guess it's not really diameter, but across. And these are then created and spaced across the cell and all connected together. So in the little squares of silicon, it's a P and N junction. So these are the whole thing is basically made of silicon, and then there's elements that are added on the N and the P type sides. So on the N side, you have elements like phosphorus, arsenic, and antimony that share free electrons. And then on the P side, you have elements like boron, gallium, and aluminum that have one less valence electron than silicon. So this basically makes the free electron side and the holes side. And then as there's movement across the junction from the electrons and the holes, this is what creates the flow of electron with diffusion across, and that actually creates the flow once it's stimulated from the solar energy.
And then something that actually doesn't use silicon that is a dye sensitized solar cell. And so I wanted to get into a little bit about them and how they relate to what we've learned this quarter. So they're kind of like a new invention, you could say, and they're a low-cost solar cell that uses dye as a light absorber, so like from the sun usually, or like from other kind of lights. And they're used to power low power electronics like calculators or remote controls. And yeah, so they're just increasing in popularity. And I wanted to talk about them a little bit and basically how they work. So, like, you can look at the little picture I have that outlines what I'm going to explain right now. But basically, the dye absorbs the sunlight, and then the photons in the dye excite the electrons, and the electrons jump up energy levels into titanium dioxide. And then that electron movement creates the electrical current. And then, so then after that dye loses an electron, it becomes positively charged. And that means that it can't absorb any more light until it gets another electron back. And so then, how do we solve that issue? The electrolyte actually solves that issue. It contains iodide ions, which ends up giving an electron back to the dye. But then the iodide ion loses an electron, which then it's actually oxidized and turned into triodide, which is a redox reaction. And so then that I wrote the little oxidation reaction there if you would like to see it spelled out. But then when the electrons actually finish going through the circuit, they come back and then reduce triodide back into iodide. And so it creates a redox reaction loop, which is actually what keeps the solar cell running. Yeah.
Yeah, and for my part, I was gonna connect like solar cells to water electrolysis. If we remember from class, water electrolysis is when we split hydrogen and oxygen ions. So like the cathode gets an electron to make hydrogen gas and ions, and anode loses electrons to make hydrogen oxygen gas. Now, how can this relate to solar cells? Well, if we use electricity with solar energy, this can make hydrogen fuel without damaging the environment, like zero carbon emissions. But obviously, it isn't perfect, and it can be affected with different factors, such as constant sunlight and weather. Now, on the other hand, if we remember from class, hard water is what water that contains minerals like calcium and magnesium ions they stay dissolved as long as they're within certain ranges of pH and temperature. If they're changing in temperature, it can form like a scale, like we can see in the picture and the before and after. Those little white spot, it's either calcium carbonate or magnesium peroxide. And this can affect the solar panels. For example, if we're using solar energy to produce hydrogen fuel, because during electrolysis, the cathode becomes basics because it's producing hydroxide ions. So if there's a change in temperature or pH in the water, this can make the minerals less soluble and coat the electrodes with scale, as we can see above, how they fill up with white stuff. And using this hard water can reduce the effectiveness of the electrolyzer and making it really inefficient.
Okay, and then for my part, I just wanted to talk a little bit about why solar cells degrade over time and like the different types of degradation that actually happen inside the cells. Starting off with why they degrade, solar cells are built to be durable, but with constant exposure to sunlight, weather, and temperature changes, this slowly stresses and wears down the materials. Bonds in the silicon break, metals oxidize, and chemical reactions slowly build up. As these changes happen, the cell becomes less and less effective at moving electrons, which basically leads to the panel producing a bit less electricity each year. And then below that, I just have a little bit on how they degrade, but I'll go more in detail when I talk about the types of degradation that happens. Okay. On one major factor of the degradation is UV. When the UV energy hits the panel, it can break chemical bonds in the silicon and its protective layers. These broken bonds turn into defects that can block the flow of electrons. Heat also contributes. High temperatures speed up chemical reactions and create physical strain inside the cells itself. This makes materials like silicon and metal break down. And moisture is another important factor. When water gets inside, it reacts with metals such as silver or aluminum. This leads to oxidation, which basically means the metal loses electrons and begins to corrode, which reduces conductivity and makes it harder for the panel to carry current. Then there's also encapsulation breakdown. The EVA plastic that surrounds the cell can slowly oxidize or absorb the moisture. When this happens, it becomes less effective at protecting the cell, which allows more moisture and oxygen to get in, continuing the degradation process. So, overall, solar cells degrade because UV light, heat, and moisture, as well as the breakdown of materials. All of these factors make the electron movement less efficient over time, which leads to a gradual drop in performance.
Sweet. Well, thank you. That's all we had. And here is our sources that we used for all the information we found in this project.